turns out that if f of xy, f being a vector field here, it has components p and q, both functions of xy, f is conservative if and only if, so this is a test to see if it's conservative. If you take dp with respect to y, the derivative of the first component of f with respect to y, and it equals the derivative of q with respect to x, then you know for sure that f is conservative. So, and by the way, this is true as long as f is defined on an open, simply connected region, and f has continuous partial derivatives. Now, okay, when you see the if and only if statement, that means the statement goes both ways. You could say if f is conservative, then dp dy equals dq dx. But the if and only if statement means you can turn it around and say, if dp dy equals dq dx, then f is conservative. Going that way is hard to prove. But going in the forward direction, if f is conservative, then those partials are equal is easy. All we're saying is mixed partials are equal, and we already knew that. Because if you think about dp dy, that's got to be the second derivative of the scalar function little f. First with respect to x, then with respect to y. Because the first component p is really f sub x. The second component q is really f sub y. So when you take those derivatives, you're taking mixed partials. Mixed partials are equal. Okay? Is that believable? That's only one way, though. Going the other way, which is actually what we want to test to see if f is conservative. Going the other way in this statement, we would want to say if this result is true, then f is conservative. And we don't have the tools to prove this yet. So we introduce it a little bit early so we can use it. So let's use it. We have f of xy equals y e to the xy I plus x e to the xy j. Show that's conservative. So we want to show, from that theorem above, we want to show that the derivative of q with respect to x is equal to the derivative of p with respect to y. You show that, by the theorem above, you can conclude that f is conservative. Okay, what function's p, what function's q? So this guy is your first component, that'll be p. This guy is your second component, that's what we're calling q, right? So we're back to taking partials. Good review for the final though, right? Yeah, okay. So I want to take, let's start with dq dx. So dq, the derivative of q with respect to x, so that's this guy. Oh, it's x times e to the xy. What do I have to do? What rule do I have to use? The multiplication rule, the product rule. So let's call the first function x, the second function e to the xy. What would the derivative look like? Derivative of the first, which is 1 times the second, plus, and then the first times the derivative of the second, that's the product rule. Okay, what's the derivative of e to the xy with respect to x? E to the xy times y by regular chain rule, right? You buy that? Okay, so what else do we want to show? Derivative of p with respect to y is hopefully the same thing, right? In fact, maybe I can change this to an equal sign. Maybe I'm so confident I'll change it to an equal sign right now. Okay, so let's make sure that that equal sign is true. So look at p up here, y times e to the xy. Once again, it's a product of two functions of y this time. So take the derivative. What do we get? Derivative of the first, which is with respect to y, which is 1 times the second, which is e to the xy, plus the first times the derivative of the second, e to the xy times, we're taking the derivative with respect to y, so it should be x that's left this time. And you can see we definitely do get the same thing. And so your conclusion is, f is conservative by the above theorem, but you don't have to say that. Now, I'll bet you could come up with the potential function just by guess and check. So remember what the potential function is. It's a scalar function, little f, such that when you take its gradient, you get big F. That's it, right? I mean, think about it. So just by guess and check, you came up with it that little f of xy has got to be, it's got to involve e to the xy, right? Because when you take derivatives, that factor is going to stick around. And if you take the derivative with respect to x to get the first component, you'll see it works out perfectly. Take the derivative with respect to y to get that j component or second component, you'll see you get the right thing. But do you think it's always going to be that easy to find a potential function? Only if you're a very optimistic person. No, so let me show you a harder example.